So there we go. That was equilibrium. Okay, so what we're going to look at next is dynamics in 2D. And when we say dynamics, you should be thinking Newton's second law. Okay, so we're looking here at Newton's second law using the summation sign. All right, so what we're going to be finding is that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. In other words, net horizontal force equals mass times horizontal acceleration. So that ought to lead you to understand what F sub y is going to be. Yep, mass times acceleration in the y direction. In other words, net vertical force is going to be equal to that same mass times the vertical acceleration. Okay, so if we have net vertical force, we have vertical acceleration. If we have net horizontal, we have horizontal acceleration. All right, so now we can reduce the following two rules governing forces relative to acceleration. Forces that are perpendicular to the acceleration the vectors will balance out. Okay? Forces that are parallel to the acceleration, vectors will add to mass times acceleration. But if the force is opposite acceleration, we're going to count that force as a negative. And y'all know this already. That's the convention we've been using. So what on earth do we mean by that? Well, now we're on an incline. And if we have a box on an incline, and you've seen this once already, then what's going to happen is we've got the force of, it says assume there's friction in the first two, by the way. So if this box is sliding this way, then what we assume is that we've got the force of friction going this way. We've got the force of gravity going straight down, in other words, mg down here. And then we've got the normal force coming out this way. Well, then what we find is that those vertical forces, which would be your perpendicular forces, you're going to end up with components for gravity. You've got one that goes down and one that goes sideways right here, and this would be theta. Then these two forces right here, vertical, which are perpendicular to the motion, because we are going to assume that is accelerating down this incline, those two guys balance. Okay, so these guys are the same. So perpendicular, you're going to get the normal force, and that's going to be equal to, well, this guy right here, which is going to be mg cosine theta. So mg cosine theta. Now, this guy right here, this chunk, is going to be mg sine theta, okay? And so if we go looking at the forces horizontal or parallel, we've got the force of friction going backwards, and then we've got this chunk, which is mg sine theta, going forward. So what we've got is we've got ma equaling mg sine theta minus our force of friction, okay? Because mg sine theta is going in the direction of the acceleration, force of friction is going opposite. Now, what happens if we have a box being pulled? This is a different one. This box is being pulled at some sort of angle theta. So we know we have an angle theta here. So what we realize is that, again, we've got some sort of horizontal component here, and we've got a vertical component here, okay? But what we also have is we know we've got mg going down here. We've got normal force going up here. We've got the force of tension right here. That's what that guy is, if it's a rope. And then we know if this box is being pulled that way, then we have the force of friction going in the opposite direction. So now, again, in red, let's talk about our forces that are perpendicular. We've got the normal force, we've got the mass times gravity, and then we've got this tension force right here too, which would be, if you think about it, this guy is going to be the force of tension times the sine of theta. Why sine? Because it's opposite. So if we're going to write this, what we know is that the things going up, which would be your normal force, plus ft sine theta, is going to be equal to mg, which is going downward. Okay? Now, let's look at horizontal forces, horizontal force of friction, and this little chunk right here, which we probably ought to define. This is, of course, going to be the force of tension times the cosine of theta. So when we go back and write this guy, we're going to know that ma, because it's moving, is going to be equal to, well, this guy's going in the same direction, so it's force of tension cosine theta, minus this guy, because it's going in the opposite direction, force of friction. Okay? Last but not least, we have a ball being pulled across the floor, so we know we've got a force of tension going up this guy, which means that we've got a component going this way. I'm sorry. We've got a component going upward this way and a component going sideways that way. Okay, so this is going to be my force of tension cosine theta now, because look where theta is. Theta's up here and not down here. And this would be ft sine, force of tension times the sine of theta. What other forces do we have? We, of course, have the ball, mg down. And if this thing is actually a ball on a string and it's not actually resting on the ground, it's just swinging this way and this way, then that's it. That's all we have. Okay? So what do we know? We know the force is acting perpendicular to the motion, because what way is the motion going? Well, acceleration, it's going that way. It's going to be swinging, so technically it's going to be swinging that way. So what's the only force we have here? Well, this guy right there. So parallel, we know that ma has to be equal to ft sine theta, force of tension sine theta. Now, in the other direction, we have mg going downward and ft cosine theta going upward. That means we've got this. We've got mg equal to f sub t cosine theta. So you're looking at these equations as perpendicular is going to be equal and opposite, and parallel is going to have your ma factor, the direction it's actually moving in. Now, if it were not moving sideways, then we would be, if it were moving up and down, then that would be swapped. Okay? So let's double check what we know here. We've got this system right here. We've got this 37-degree, it's being pulled at a 50 Newton force at a 37-degree angle. We've got a coefficient of kinetic friction, and that is 0.4. Draw the other forces acting on the box and write two equations that relate the forces on the box. Okay, so we know we have mg acting downward, and that's going to be 10 times 10, which is 100 newtons. We've got the normal force going upwards. We're not going to say that's 100 because it's not necessarily. We've got components to this guy, one going this way and one going up. So this is going to be 50 times the sine of 37. And this, of course, is going to be 50 times the cosine of 37 degrees. Now, the only other force we have acting is if this block is being moved that way, which we're pretty sure it is, since it's being pulled that general direction, is we have a force of friction, which is this way. So let's see if we can figure out what's going on here. What is the normal force acting on the box? Well, the normal force is a perpendicular force. So that's this guy. So we also have to take into account this guy and this guy. So let's write it according to that. So we have the normal force up plus this 50 sine 37, that's also up, which has to be equal and opposite mg. So my normal force right here is going to be equal to mg, which we said was 100 newtons, minus 50 sine 37 degrees. So that's going to be 100 minus 30, which is 70 newtons. So the normal force is 70 newtons. Now what's the frictional force acting on the box? Well, the frictional force, if you remember, is mu, kinetic since it's moving, times the normal force, which means it is 0.4 times that 70, which means it is 28 newtons. So the force of is 28 newtons. Okay? Now what's the acceleration on the box? Well, the acceleration is going to come from the other direction, if you remember. Acceleration is going to come from parallel, which is just these two guys. So what do we get? We get ma is equal to 50 cosine 37 degrees because it's going in the same direction. It's going this way, acceleration's going this way, minus that force of friction. So mass of this guy, if it is a box, it's a 10 kilogram box, so we've got 10 times the acceleration, which we don't know. 50 cosine 37 is 40, minus the force of friction, which we just found, which was 28. So we have 10A equals 40 minus 28 is 12, so A is equal to 1.2 meters per second squared. So you can see how you can kind of do this in steps. What's your normal force? Why do I need the normal force? Because the normal force is going to give me a frictional force, and my frictional force is going to help me find the acceleration of the box. And that's not what we got. We got the normal force was 50, was mg minus, or it was the same thing. All right. So now suppose the box is being pushed with a 50 Newton force instead. Okay, so now it's not being pulled, now it's being pushed. The normal force, if we look at this whole thing, and you got to think about it, you've got mg acting downward this way, you've got the normal force acting this way, but now this arrow is downward and this way. So my normal force, which is upward, is equal to this 50 sine 37 degrees plus mg, because they're both going in the same direction. Now, if you look at the left, this time it's mg plus. So the normal force is now more, okay? Because the normal force opposes both the push, and this is the downward part, and mg. What about the frictional force though? If the normal force is more, we know that the frictional force is equal to mu times the normal force. So the frictional force is now more. Since the force of friction is directly proportional. So if the frictional force is more, I want you to think this through. That means it's gripping harder, which means your acceleration, if that makes sense, should now be less. Okay? Now why is that? Because MA is now going to be, because we think this thing is still going this way, MA is now equal to what? So we've got we didn't finish drawing this, so we know this chunk right here is going to be 50 cosine 37 degrees. But since it's moving in this direction, frictional force is going to be the opposite way. Okay? So this is now going to be 50 cosine 37 minus the force of friction. Whereas if you looked at direct, same thing, but this is going up. The net force, because let's not forget what this is. This represents F net, doesn't it? The net force decreases. Therefore, since my acceleration is equal to F net divided by m, it goes down. Okay? So, when an object is on an inclined plane, the weight force, or gravitational force, is the one that makes the oblique angle with the acceleration. Okay? What does that mean? That means that this is at the same angle that this is. Those two are the same. Okay? So now, what all do we know here? If we look at this, we've got mg going downwards here, right? No friction. So we have force normal here. So all we really have, we know the acceleration is going to be down the incline because it's going to slide down. So what we know is that we've got a vertical component and we've got a horizontal component right here. So the normal force on the block, which we're looking at right here, which is a vertical force, has to be equivalent to that force right there. Well, that force right there is color coding here, mg cosine theta. So, force normal equals mg cosine theta. Okay, what's the acceleration of the block? Well, the acceleration of the block is going to be the thing that was in the direction of the acceleration, which this case would be what? mg sine theta. Okay, so MA, sum of forces, which is equal to MA is equal to mg sine theta, and the m goes away. So the acceleration is just g sine theta. Now, if we have friction added in, that just gives us another layer. It does not affect the normal force. The normal force is still going to be, if we've got mg acting downward, normal force acting upward, but what do we know? We know the acceleration is downward, so we also have a frictional force, but that frictional force doesn't affect. It's perpendicular to the normal force. So the normal force is still going to be that mg cosine theta component, the one that goes this way. Here's theta, this is mg cosine, okay? But the acceleration of the block is going to decrease. So what we know is the sum of forces, which is equal to MA, is no longer just equal to the mg sine theta component. It's going to be that minus the force. So it is minus the force of friction. And we know what the force of friction is. Force of friction is the normal force times mu. So we're going to plug that in. So we're going to get MA is equal to mg sine theta minus mu times the normal force, which is mg sine theta minus mu mg cosine theta. And this is ma. Well, look what's in all of them, guys. The mass. So m cancels out, and we get acceleration is equal to g sine theta minus mu g cosine theta. Okay? Okay, we're almost done here. Last set of examples. Determine the normal force on the 10 kilogram mass in each of the following diagrams. Okay? So, the normal force we know is here. All right? That means, and what we've got going down here is mg. So it needs to be, we need the component of that. This is also 37 degrees. So we know this is going to be mg, it's adjacent, so cosine theta. So the force normal, if we look at it, this and this are opposite and equal each other, is mg cosine theta. So that's going to be mass is 10, g is 10, times the cosine of 37 degrees. So 100 times the cosine of 37, this would end up being, which is 4/5, which end up being 80 newtons. There's my normal force. Okay, now, how do we find this guy? We know that let's assume we have friction in the second one, okay? Just to make it easy, or harder, I don't know which you want to consider. All right, so what do we have? We have 50 newtons being pulled this way, okay, but we want the normal force. So we know we've got mg this way, we've got the normal force this way, and then we've got a component of this, which would be 50 sine 37 degrees, okay? And then this one would go this way, not that we need it. So the normal force plus this 50 sine 37, because they're both going up, has to be equivalent to mg downward. Well, okay. So normal force plus 30 equals mg, which is 100, right? 10 times 10. So the normal force in this case is 70 newtons. Determine the acceleration of a 10 kilogram mass. Okay. So, did you see that it didn't even matter what friction was? Because it was in the wrong direction, wasn't it? So now we know we have friction, and now we want to know the acceleration. So it does matter with the acceleration, doesn't it? Because you know what we know? We just found that the normal force for this was, what, 70 newtons? We found that from the previous problem. It's the same setup. Okay, that's going to help me, because what that's going to tell me is that the force of friction is mu, which is 0.2, times that 70 newtons, which is going to be, what, not 3, 14? 14 newtons. So the force of friction is 14 newtons. Now, why do I need to know that? Because I need all of the forces acting in the same direction as the acceleration. So now I need this guy, which is going to be 50 cosine 37 degrees. And I know that I have a force of friction acting this way. So my MA is equal to that 50 cosine 37 minus the force of friction. Okay, so MA would be 10A. This would be 50 cosine 37 would be 40 minus the 14. So 10A is equal to, what, 26? 10A is equal to 26. So A is going to be 2.6 meters per second squared. Okay? Object accelerates horizontally, so we know our acceleration is in that direction. So what do we know here? We know this is mg, and we know we've got a force of tension going this way. So if we're looking for acceleration, we're looking in the same direction as acceleration, which means we need the horizontal component of this force, which would be the force of tension sine, because it is opposite of 37 degrees. So we know that MA, since this is the only horizontal piece of this, has to be equal to the force of tension times the sine of 37 degrees. Okay, well, I don't know what the force of tension is. So you know what I'm going to have to do? I'm going to have to use the other direction to find that force of tension, because I know M and G. So this is going to be the force of tension times the cosine of 37 degrees. So I'm going to take this and set them equal. So mg equals force of tension cosine 37 degrees. So this is going to be 10 times 10 equals the force of tension cosine of 37 degrees divided by the cosine of 37. So the force of tension is going to end up being 100 divided by the cosine of 37. It'll be about 125.2 newtons. So now we have 125.2 times the sine of 37 degrees and 10A. So 125.2 times the sine of 37 degrees divided by 10 gives me about 7.5 meters per second squared. Okay, so there's my acceleration. All right, calculate the acceleration of these blocks. Start with free body diagrams. Here we go, last example. So for the 8 kilogram block, what do we have acting on it? We have the force of gravity acting downward. We have the normal force acting this way. We have tension this way. Assuming the, and look, we've got a mu right here, so we know that we also have the force of friction acting this way. So there's my free body diagram for that one. And this is force normal 1, and this is force of gravity 1. Yes, I am using subscripts. Now, we know for the other block, we have the force of tension. Notice I'm not using sub 1 on that one because it's the same tension, because it's the same string. But on this guy, I have the force of gravity sub 2. Okay? Because they're not the same mass. Use your subscripts wisely. So now, if I'm doing a free body diagram for the AP test, I don't add anything else to this. I do not add any kind of components to it. Okay? So, the forward force, we know what's going to happen here. We know that this block is going to what? Object accelerates downward. So my acceleration is downward, which means here my acceleration is up the ramp. Okay, up the incline. So let's start with the 12 kilogram one. What's going on in the positive acceleration? In the positive acceleration, we've got this going on right here and then that going on right there. So here we go. We know that that's going to be what? mg. Let's make this big mg, and let's make this little mg. So we've got a forward force of big mg here minus the force of tension is going to give us big M A. Okay? Forward force on the 8 kilogram. Forward force on the 8 kilogram is going to be, and we'll do a different color for this one. We'll do green for this one. Actually, I'm going to do red. Since acceleration is going up, that would be this guy. Here, we'll do this in red. This guy, and then the component of that guy. Well, what is the component of that guy? This guy's going to be this way. So this, which is 37 degrees, right? That's 37 degrees, is going to be mg sine 37 degrees. Okay, so, but forward is only the force of tension. Backwards, we have the force of friction. And we have mg sine 37. That is going to be equal to little m times A. Now, for the system, all right, for the system, remember what we can do here. Okay, so for the system, all we have to do is do a little bit of adding. If we add these together, right, we learned this. Force of tension is an internal force. That is an action-reaction pairing. It goes away. So we're left with big mg minus the force of friction minus mg sine 37 degrees equals big M plus little m times the acceleration of the system. So now it says show your process for solving the system acceleration and then the tension of the string. Okay. So we have big mg minus the force of friction minus mg sine 37 degrees equals big M plus little m A. So now the first thing we need to know is that the force of friction is equal to mu times the normal force, correct? So we need to know what the normal force is. Well, the normal force comes from, if you remember, comes from the perpendicular guy right here. Well, what is that guy right there? This is going to be mg cosine 37 degrees. So we know that the normal force is, this is going to end up being mu sub k mg cosine 37 degrees. So let's plug it all in. We've got mg, big mg, minus mu sub k little mg cosine 37 degrees minus a little mg sine 37 degrees equals big M plus little m A. So now I'm just going to plug in all the numbers. Big mg, this is, big M is 12, so 12 times 10 is 120, minus 0.5 times little mg, which would be 80, cosine 37, minus little mg, which would be 80, times the sine 37, equals big M plus little m, which is 20 times A. If you work that whole thing out, you get 40 on this side equals 20A. So you get an acceleration of 2 meters per second squared. Boom. Okay? You've got to be able to do these types of problems where you're setting up forward and backwards on the one weight, forward and backwards on the other mass, and then forwards and backwards for the system. Okay? This is the same thing we've done on these. It's just in 2 dimensions now instead of 1. All right, that's the end of your notes.